Thank you all. Again, I'm presenting joint work with my colleagues Amanda Boone, Niku Ranjit, and myself. One of the things that's increasingly prominent at Stanford and other universities is that more and more classroom lectures are being recorded. And those are to facilitate supplementary degree programs, but also to act as a learning supplement for students. And one of the things that I've found really fascinating by is how different the in-person experience of viewing a lecture is, and how different, say, a video-based interaction pattern looks like. So what do we think sort of the distribution of attention looks like when a student is watching a stage-on-stage lecture? This is a bit of a straw man, but I would contend that it's uniform. That no matter how compelling or interesting the speaker is, ultimately you can only spend 1 second per second on whatever the person's saying. Whereas when we can look at a parallel course with video interaction, we see that the distribution actually looks quite different. That there's heaping, that there are areas where students pause and reflect, where they rewind, they fast forward. And what's really interesting about this is we've talked a lot about recommendation engines in the past, but one of the things that Facebook and YouTube and other video interaction platforms do is they actually take this clickstream behavior to create a histogram of sorts to try and understand these are the hotspots and areas where people interact with videos. And from an educational context, you can imagine that this might be useful for identifying the most relevant features or identifying areas where students might be confused or rewinding. Particularly because MOOCs are so focused on video-based interaction, I'm just sort of wondering can we actually try and build this plot before students see it? And there's been some prior work in this field, and what they've noticed is that attention tends to heap across slide transitions. Other individuals have tried to model clickstream behaviors as sort of a grammar using regular expressions and syntax trees. But what's really surprised me is that people haven't actually looked at what the instructor is saying at a given point in time. And the only reason why I can think about that is because transcription costs were exorbitant back then. But thankfully, Berkeley got sued about 18 months ago, and as a result, almost all MOOC content now has very clear and granular transcriptions of what's being said with it. So the preliminary work we're doing is we're trying to figure out which behaviors, play, pause, rewind, fast forward, can be predicted, and what features are predictive of these clicks, what features are predictive. And we took just one sort of simple MOOC that was taught in parallel at Stanford. Roughly 77 videos that comprised 14,000 utterances, and we just partitioned them into train, test, and dev sets. And to give a little bit of a perspective on how salient transcripts are in this type of interaction platform, it's kind of like karaoke. You can see exactly where a student, what is being said when. So the bolded text right here says that they are looking at the distance points from generating an SVA. And we just generated your standard NLP features, bag of words, Luke, just sort of very dumb topic models of what's being discussed, as well as the reading level and reading level of the text. The one feature that is kind of education related is we looked at cosine similarity between the content being spoken as well as all of the various assessments that are important to the course. We did your standards, shallow and deep architectures with our sort of dumb null model being our counterfactual. And what we found was that right now, at least, with just this little bit of data, we really can't predict pause and play behavior. But video seeking, so that fast forwarding and rewinding behavior, we see about 10% improvement compared to our baseline model. And if we look at our relevant features, what we see is that it basically is a student is searching for glossary-based terms. This was a statistics course, so they're looking for looking for that terminology, probability, alpha, beta, those sorts of things. So very sort of intuitive. Admittedly, we're not talking about very high levels of performance involved. So next steps are we'd like to try and train this on a larger corpus. So ideally, LinkedIn Learning, if you are ever able to provide any data, or Udemy, or any of those in the audience, I would really love a new corpus to start trying this out. All right, thank you so much.
Time for one question.
I couldn't understand when you said you could predict fast, like the rewind behavior. Like, can you give us like an absolute sense of how accurately you could predict it?
So only about 10% better than like your done model just taking whatever the sample averages for the entire video.
Okay.
So not a very big improvement at all right now.
And do you think that's just so? Okay, but is the null model just, does it learn like certain sections tend to be rewinded to more often, or like how sophisticated is the null model?
Just straight line.
I don't know, just straight out.
Straight line.
Uniform probability of rewinding anywhere.
Exactly.
Huh. So there aren't certain sections that just tend to be more rewound than others, like that you could just learn, like just literally by counting or something like that?
There are. Part of the issue here is that, again, it's a MOOC audience, so there's huge dropout. When we subset this to, say, active and engaged learners, we actually can perform much better. But right now, there are just so many individuals who are just in that early stage of, I'm pressing play, I walk away.
Well, okay.
Yeah. Well, thank you so much.
Thanks.
Thank you.